We can talk about generalized policy iteration, where essentially learning and reinforcement learning, or learning in general, you could argue, where you have to learn from experience, has these two stages, right? Where you've got to evaluate the policy you currently have. So whatever you're doing, you try to see, is this a good way of doing it? How much does it reward me? Right, so that's that policy that you're starting with, pi, and pi tells you what action to take given the state of the world you're in. And when you evaluate it, you end up with a value function. So this value function could be v or q or some other kinds of representations where you say, given some state that I'm in, if I follow this policy going on into the future, here's how much value I get. And that could be money or expected reward or preferences and utilities. But it's your gauge of whether the policies, if one policy is better than another, right? Because really what you're trying to say is, should I change the policy or is it good enough? And then once you have an evaluation of that policy, you can then form a new policy. And in the basic form here, we talk about just kind of being greedy according to that value. Because once you've fully followed out a policy and seen how it behaves in the whole system, in the whole game or environment, now if you compute the policy that kind of this value function implies, it might be a different policy, right? So I guess your robot is learning to move around in a space, and it's got, in the previous round, it got really good at opening doors, right? And some other part of your policy has never been used in another part of the room that didn't have doors. But now when you evaluate the policy going forward and seeing how much what it gets you in the long run, you'll realize, oh, now I can get out of this room and get to another room and get the thing I'm supposed to be acquiring, the robot, right? So suddenly your value of this policy is now much better because in one area of the state space, you've learned to open doors versus before, right? So when you go and get a new policy now based on this, you have a whole new world of things, and that policy might tell you, well, first thing, get out of the room, go to the second room and do something. So the policy changes when the value function changes, and obviously if your policy changes, then the value function that it evaluates it will be different, right? So you just go in this cycle, and the idea is that they should converge, right? And if it's a true evaluation of it, the policy value theorem is going to be, it says that we're going to be reducing the difference between the value functions over time, and eventually when you get a greedy policy from this value function, it'll give you a policy that won't change, right? And so once they stop changing, then you've reached the optimal policy. Now in practice, you're not gonna go all the way to optimal usually, because the world is a very big thing. So the initial problems we're gonna give you for the next assignment are small enough you can solve them exactly and compare, but then you make it a little bit bigger and it becomes very hard. And it doesn't have to be too big for that to happen, because you're always searching over kind of the exponential space of like all states mapped to all states taking actions in those states. So it grows a lot. But there's a general concept that'll apply to a lot of algorithms and generally holds. In the algorithms we've talked about here, they are synchronous, so they're kind of going through, if you recall, or if you don't recall, because we didn't see it, I'll go back and show it. For policy iteration, which is really the core one, we have all these steps in here, right? We do evaluation of the policy, where we have a loop where we go over all the states, and for every state we kind of compute the value. We use that Bellman equation in the center, update its value, and when I said the difference is kind of converging down to zero, you have this difference, the delta that you're computing, right? And once that delta becomes very small, below theta or epsilon, as I was saying in the video, then you stop, right? So your evaluation kind of goes until it's good enough, or it seems to stop changing. Similarly, the policy is going to be updated, and you're going to keep looping until that stops changing, and you cycle in between these two, right? Then you have initialization step. Where was I going with that? Right, this is synchronous, right? You go through all the states over many times until you get a good evaluation of the current policy. And then once you have that perfect kind of value function for this particular policy, then you try to come up with a new policy, and then you go back and forth. Right? So that's very strict and synchronous, meaning that they happen at the same time. Right? So all of these steps, you completely do one before you do the other. But actually, the theory doesn't require that. If you jump back and forth between them, you can still converge in the same way as long as you stay on these lines, and as long as you guarantee that every once in a while you do visit all the states. Right? So it's kind of like, instead of these big jumps on the lines, you could have lots of little jumps, but you have to guarantee that kind of after a while, you actually do visit all the states and come back to them. As long as that's true, then the theory and the algorithms still work. So you could have a kind of a more greedy version of these algorithms where instead of going through all states, you pick a state at random and you apply the backup, which is what we're calling that, applying the Bellman equation to compute the value, right? And you do that for that random state. And then you may move to your next state and you update them as well. But as long as you have a part where you're randomly picking some states or sampling from the states in a way that if there's some state that's always being left out and you never quite get there and it always gets left out and so we don't know its value, maybe it's a really fantastic place to be, maybe it's horrible, but you never tried so you don't know, right? So as long as you have some element of randomness so that this exploration guarantees you'll see everything, it would still converge, right? And in practice, this would probably converge a lot faster, right? Because you're actually going to be focusing on the things you need to do and covering a lot of it. And many states actually aren't that important to get to, right? Every corner of the room that you've never been in for the robot probably isn't that important unless it is, right? Unless it's the place where the charging station is or there's a hole in the ground, right? But most of the time that doesn't happen. And so in practice, these asynchronous things often work much faster and still converge, even though theoretically they should take longer. Yeah, and so you can even use it where you pick the state to back up based on ones you need, right? So you can start thinking of using the probability, your estimate of a state, how many times you've seen it, to choose it based on its importance or knowledge that it will increase for you. So that's another kind of concept to kind of know what that. And so here's what this lecture was covering in terms of how to solve the value functions for MDPs exactly. And the reason that links onto what will come in the next set of lectures is that it's actually not very efficient, right? Because the number of states that we're considering here is exponential. Like you have to, the number of entries in the value function is exponential, right? You have to update every state for every possible state it could reach next for every action you could take from that state, right? So it's very inefficient, and even a system with millions of states, I think, is a bit bigger than back then, but tens of millions, hundreds of millions is still too big to solve exactly, right? But the same ideas are going to be used to approximately solve it. It's just that these representations, so the value function, rather than being an exact table, is going to be a function that approximates that value, and you can fill in the blanks by doing interpolation in that function. That's why neural networks work so well for that, because they automatically interpolate different states that they've never seen, different inputs. So we'll be getting to that. And yeah, and then when you do that, the guarantees that you have about it converging kind of change. So you need to be aware of that, right? And so the notes ahead on there, and this cursive dimensionality kind of term comes up a lot, and that's related to that exponential explosion in the number of entries you need to track when you're optimizing it. So that was all there was on that that section, and I guess this is a summary of the things from that part in terms of what was important. And I've highlighted the ones that are kind of more important in terms of what I think are important for the class and for your usage actually in the real world, because they're things that the concepts that will be used more later. So if there aren't any other questions, I'm going to encourage people to kind of go look at those videos and then continue working on the assignments, kind of get ahead on it. And we'll see you all on Piazza. And let us know if there's any ways to improve kind of the process and the engagement for the course. I know we're kind of trying to do that on all the courses in the department. If you've got ideas or seen things that have worked other places, please do let us know. Okay, thanks a lot.